One 1,000. Two 1,000. Okay. We're very close here. Here. I can't even count. Those were just random words I said.
Where do you memorize?
Words I memorized. How I got through kindergarten. So we're here. There's gonna be no labs. What? Why did you even come? Do you like being in person, right? That way we can do lecture tutorials together.
You should tell me, but it was yet. Because my other class goes online.
I mean, so we had a bet in the office how many people would come. And currently I am losing that bet.
You said all of them?
I said 7. There's 8.
Bye, everybody.
Bye, everybody. I think there's actually one more. There's 9. So I think I wait. Did I win that bet or do I forgot what the rules were? Anyway, so we're not gonna do a lab today. The lab that I had planned is one that I'm designing, and considering we just did one that I'm designing, you know, kind of worked okay. We're gonna let that one slide. Everyone who did that lab will get credit for it, regardless of the exam. You'll just get an immediate 100 for participating in a brand new lab and be part of my lab development. Because if you didn't quite get it, right, that's on me. That's not on you. So I noticed that sometimes I didn't explain it good. So we're gonna work on that development. Okay. And then next week we're gonna do, it'll be 84%. So we'll have some mostly full moon. And so if it's possible, we'll go and we'll look at the moon. We had an open house on Thursday, and it was pretty nice, right, Tori? Was there? And at some point we should talk about what those actually mean. So I'll pass out the lunar observations and the deep sky observation, and you'll make some fun drawings of the things that you saw. That's essentially what they'll be. So I'll print both of those for next Monday. And then you can turn those in and you'll get 100 on those if you've ever gone to any single open house. Okay. Okay. If you don't turn those in, that's fine, right? There's no like requirement that you have to spend class time outside of class. But this would act as an extra buffer, right? Bring those grade points up. Questions? Okay. So let's jump into content as advertised. Some people think this is the best class of the semester. I personally don't think that's true, but we'll see how you feel.
Which do you think is less class?
I think all of them are tied for first.
So you're saying this one's also class?
No, I'm kidding. So there's a class that, or there's a lecture that I give which talks about why we don't see aliens or we're not aliens with this. That's my favorite class to give. This is one of my top 5. Okay, and it's basically what happens to stars when they give up on life. Okay. Can we hit the lights just for a few minutes? What is this? Star. Nebula. So nebula is a great answer because it's very vague and it doesn't mean anything. So what does nebula mean, Isabel? Fuzzy. Specifically, it means cloudy. This is a Latin word for like cloud or mist. But what am I actually looking at if I wanted to be more helpful? A supernova? Okay, interesting. What's that?
It looks like it's forming.
Forming. Okay, so you're gonna go with like collapsing this way? Yeah, this is kind of weird, right? Which direction is time flowing? Is this falling in or is it pushing out? Yeah. Well, like, you know, if I watch the picture, is this gonna do this or is it doing that? Any guesses? Raise your hand for explosion. Raise your hand for contraction. Okay, all right, fine. No, just kidding. Okay, so in this particular circumstance, this is an explosion. Is it? Yeah.
Why is it so
Why is it so circular?
organized? Yeah.
Yes, so that's exactly why, right. The reason we know this is an explosion is because this is a perfectly round star going bang,
Ba-bang.
bang. Okay, this is actually not in the visible. It's a false colored image. If you look out in this part of space with your eyeballs, you will see nothing. And this was difficult to find. So in fact, this is a supernova that happened, or this is what we call supernova remnant. The supernova occurred in 1006 AD. And Chinese astronomers can pinpoint it exactly. There's many records about how bright it was. So you could see this during the day. And it was bright enough at night that it was like the moon was at a quarter of its fullness. So you could like read at night by this thing's light. So when supernova go off, they're one of the most bright things in the night sky. And if they go off very close to you, they can kill everything on Earth. That's fun.
Yeah, it's not fun.
So fun. Okay. So thankfully that didn't happen here. Obviously, this is far enough away because we're all here. So here's this is a supernova remnant. These little pieces here, they're not stars, they're just little parts of hot gas. Because every photon that you're seeing here is an X-ray. They're X-rays coming at you. So this is the shock bubble. We learned about shocks today. So this is really hot material moving into a cold material and heating it up as it smashes in. Okay. Okay, and we're going to talk about how this happens in the first place. We can have half the lights back. Thanks, Caesar. Okay. We talked about this. Everyone's super familiar with the HR diagram, right? And then we know, of course, that we live here, and then we run out of hydrogen to burn, and we go up here, and we burn it in a different way, right? And then we say, no, it's not worth living anymore, and we come down here sometimes, right? Okay. How big are these ones? Small. Good. About Earth size. So take a star, squish it to Earth size, and you get a white dwarf. Okay.
The white dwarf is like the core, right?
Yeah, when we say the core, we're thinking mostly carbon, right?
Yeah.
In this particular circumstance, take something that's comparable to the sun, turn all of the hydrogen into carbon, and then shrink it, and that's a white dwarf. White dwarfs, usually something this size, did not come from a one mass sun. Why is that? What's that? Oh, let's think about how it got there.
It blew off its exterior shell.
Blew off its exterior. Remember you said that it's the core? So it's the one mass core that's left over of a larger mass star, generally speaking. And that extra stuff blows off in the planetary nebula. And it leaves behind a one mass white dwarf. So you'll notice on here, right? We'll talk about, say, the sun, right? Well, so that's a one mass sun. Good. But was it always one mass? No, probably not. It probably started with a little bit more mass and it'll end its life with a little bit less mass, right? And as it goes through this process, it will lose mass. Right? Questions? Okay. All right. Higher mass white dwarfs, though, they're smaller. Why is that? And what happens if you get more dense than 1.3 suns, M suns?
It becomes black hole or neutron, sorry.
Okay, well, which one? We're gonna find out, right? Okay, let's find out. So we talked about the white dwarf limit. And that white dwarf limit is about 40% larger than our mass of the sun. And as it approaches this limit, electrons have to move at the speed of light. So this is called the Chandrasekhar limit, the white dwarf limit. And it says after that you can't have any electrons in this area. Okay. So what happens to a white dwarf if it passes that limit? A, explode, B collapse into a neutron star, and C gradually begin to fuse carbon. We all did the readings. We all know this, right?
Yeah,
Yeah. We don't just show up to class, right? No, we do the reading ahead, right?
and we do them.
Oh, and we do the homework. Yeah, we do the homework for sure on time. No. Move your fist when you're ready. Let's vote on 3, 2, 1. Are you choosing choo choices? Okay. So why do you like 2 choices?
Blow up or collapse into the neutron star.
Yeah, so that would be like a trick answer, right? So in fact, it is the trick answer. So first it collapses, right? Because the electrons are what's holding it up, the electron degeneracy pressure. And when you put too much mass onto it, you suddenly take protons and create, by smashing electrons into the proton, you make a neutron. You make a neutron star. But what happens is then it shrinks. And it falls, and as we said, when things fall onto something heavy, just like they fall onto this ball, right? It bounces back off. And then it explodes in a type 1A supernova. Okay? Sometimes those are cataclysmic. And we'll show that example in a few seconds. So yeah, exactly right. So if you look back here at this example here, where's the white dwarf?
The white one.
Yes, trick answers today.
It's probably in the middle.
Trick answers. It's gone. This one was cataclysmic. There is no white dwarf. So this is a really important thing that can happen. Sometimes supernovae are so powerful they destroy the star that created them. Destroyed. Okay. So it's gone. When you look at this part of the sky in the visible, there's nothing there. Huh? That's weird. We'll see how that happens in a few seconds. Okay. So we talked about this, right? We talked about the fact that we build up core, stuff falls in, bounces off the hard core, and you get a supernova. Okay. Here's the supernova. Take the electron, smush it into the proton, get a neutron. Okay. Sometimes you get a neutron star. Okay. Neutron star is different from white dwarfs, made only of neutrons, no chemical in there. Okay. Yeah.
So is it like dark? You can't see it then? You see it.
Still hot. Still hot. You can still see neutron star, just made only of neutrons. Yeah.
It's where the majority of neutrinos come from.
In this process, well, so you get neutrinos here inside of the sun when this happens naturally. So this happens inside of the PP process, right? When you have protons and electrons creating neutrons, you get out a neutrino, right? Or in the CNO cycle in other stars, right? But this in a supernova is like one bright light and only for a little while. So depending on the type of supernova, sometimes they're as long as a few weeks, sometimes they're as long as 3 months. So the one that I showed you at the beginning, supernova 1006, was bright for a 3-month period, and then it was dim, and then was bright again for 18 months, and then was never seen again. Yeah, right? Yeah, these are fast explosions, right? It says the death of a star and the complete annihilation of everything that it ever knew. So if, for example, you had a planetary system around a supernova, that planetary system would be gone, right? How big is the sun before it goes supernova if the sun gets to red giant size? People remember? What, say that again? Jupiter. The radius is out to the radius of Jupiter, right? So now imagine that falling in, bouncing off the middle, and going back out again, right? Everything's gone. Okay, the pictures are beautiful. You know, looking at supernova evidence is awesome, and you can see them especially with telescopes that, you know, we pay lots of money for, like Hubble, Spitzer, you can get really cool images. This one here, you can see a neutron star in the middle, so just like you asked, what's the color? Just like bright and stuff and hot.
Okay.
Okay, is this neutron doing fusion? No. No, what's heating it? Or another way of saying that, nothing, right? It doesn't have its own internal source of heat. It's just hot from the fact that it was hot, right? It's cooling down forever and ever and ever. Right? So if you wait a really long time, you look at a neutron star, it looks like nothing. Good, exactly right. So once it's cooled down, you wouldn't see it anymore. Just a neutron ball. Okay, how big? Really big. Big, really big?
The neutron star.
Neutron star, yeah. How big neutron star?
Oh.
No, that's what's the size of Earth? White dwarf size of Earth. Neutron stars are smaller, so I hear moon. Okay, let's hold on to those for a second. Here's another one. This one's very famous. What's this one? Everyone knows that. Good. This is why when I give an exam and everyone passes, then I realize that I gave out the solutions too. Okay, so this one is also great. You could see this. This is I think we talked about this when we talked about ancient astronomy. This one, amongst many, is a version of what we call ghost stars, or stars that appear and then disappear forever. And you can look at the pictures, you can see the size, you know how far away it is, you know how fast it was going. Right? They can model all of that. This one's more beautiful, I think. Look at that filamentary structure. Nope. Okay. So how big do we think neutron star? Bigger than the moon, smaller than the moon? Bigger than the moon? Smaller than the moon? Okay, people for smaller than the moon. What's your votes? What do you give me an object? Mercury? Which one's bigger, Mercury or the moon? I don't know. That's not what I learned in this class.
I want to see Mount Everest.
Mount Everest. Ooh, that's pretty small. You want to take an entire star and put all of the mass into Mount Everest? That's your claim, dude?
Turn it into black hole.
Well, we're talking about neutron star. Oh, you keep wanting to go black hole. We're not talking about black hole yet. Black. Does anyone like David's idea? Maybe? 2 maybes? The neutron star is about the size of a small city. You could drive across a neutron star and be home in time for dinner. What do you mean you built puddles? Oh, interesting. Yeah. Huh. What would the surface gravity be on something like maybe I'll write this as a homework problem. Okay, here's the force of gravity, right? G what?
And then.
MM. Big M for the M of the star. Let's not do that actually. Let's just call it star. This one will be us. I'm not gonna put subscripts, even though I should. And then what's down here? Square. Very good. Okay, and the acceleration that we feel, we call it little g, like this. That's usually the force divided by our mass. Right? So we can write it like G big M over R squared. Radius is small. Yeah, that's true. So let's do a ratio here. What about the ratio of the neutron star? The ratio of the Earth, maybe?
Yeah.
Okay. If I do this up here, mass of the neutron star, the radius of the neutron star, mass of the Earth, radius of the Earth. That's very convenient. I have the mass of the neutron star, the mass of the Earth. Then I just flip these. Radius. Oops. radius of the Earth squared over radius of the neutron star. Right. What's that ratio, you think?
Lot bigger than one.
Big number. What about this one here?
Big.
Small, super small.
No,
it's still-
big number.
LA, it's still bigger than one.
The Earth radius is bigger than the neutron star.
Yeah, right? So is this number bigger than one or smaller than one?
Big.
Big. And it's squared. So it's big squared. Okay, so big times big squared, that's gonna be a big number.
That's a huge.
Big cube.
Oh, let's calm down, folks. Okay, so maybe you find that out for homework. You tell me whether or not you could drive your car on the surface of a neutron star. For sure, for sure, for sure. I mean, it's a Toyota, so it's really well built, you know? Okay. Yeah, so I could get here. Inglewood. That's the full size. Yeah. No traffic, only 4 hours of traffic. Okay, so what do neutron stars look like? Well, this is how you find them. I'm using a radio telescope in 1967. Jocelyn Bell saw this really weird pattern. And she noted that there was these regular emissions. And she was like, dang, look at how close that is. 1.337301. That's the level of precision and how regular these pulses were. Okay. And what she noticed was that these pulses were coming from a spinning neutron star. What's actually happening? So just like a lighthouse that is like flashing at you, there are jets that come off of a neutron star. So here's the neutron star in the middle, okay? And this material is either falling onto it, or it has a strong magnetic field that's channeling whatever is on the surface here into beamed radiation. Spinning like this. Okay, and then we're just happen to be in the way of it. Okay. This idea, this pulsar thing, is really important for navigation. So let's say you wanted to tell aliens where we were. How could you do that in space? Well, what I want to let's say I send something on a spacecraft. I want to put something on a spacecraft, and you're gonna find it somewhere where you are. Okay, you're gonna only find the spacecraft, and you want to know where it came from. So that can change, right, depending on what path it took, right? You can give that alien very specific coordinates to where we are.
Left at the black hole.
Left at the black hole. Well, what black holes, you know, they're hard to find. We'll talk about why we don't see them very often. But instead, we can think about, okay, let's say I have a pulsar here, and I have a pulsar here, and I have a pulsar here, and I have a pulsar here. Okay. This one is pointing like that. This one is pointing like that. This one is pointing like that. And this one is pointing like that. And let's say this is us. Pulsar's timing, speed at which it rotates, is so well known and with so many digits of accuracy, see, that we can say to an alien civilization, find the one with this timing here, this timing here, this timing here, and this timing here. And where they intersect is us.
We have the Tesla.
What's that?
We have the Tesla.
The what?
We have the Tesla there on Earth.
The-
Yeah. We can do.
Oh, okay. Lost me. Okay. So this is found on something called the golden record. So if you what? Yeah, so there's a piece of vinyl on the Voyager spacecraft that tells aliens, one, what we look like, how to do math, and how to find us. And if you look very carefully, no, you have to teach them this, right? Because they might use different numbers, right? Even on Earth, for example, the reason that we have 60 in an hour is because stupid Sumerians and Babylonians wanted to count to 12. Now I like counting by 10. Some people count by twos. This dumb computer that always fails counts by twos. Okay. So anyway, if you look very carefully, and you can look this up on your phone because I should have thought about this beforehand. The picture that's on here, picture that's on the golden record, has these markings. And each one of those markings tells you the pulsar timing so that you can find the Earth. And just in case you get lost and you forget everything in space. They should pay me for sci-fi stories. That'd be a good one. You like wake up. Oh, I only use the record.
It was already used to.
What's that?
The golden disc, it was
Yeah.
already used to, it was used to Transformer E-Force.
Don't make me know that. I'll jump off something. Okay, so here's the pulsars. Okay. Could there be neutron stars that appear to us as pulsars, but not to other civilizations? What do you think? Let's debate this topic with a friend. You don't have a friend. You can- About the what? Okay.
Are they included?
Well, Pluto is included on what our solar system looks like, but it's not on the direction. Yeah, but that's like giving them an idea of the things that we know at the time. Right? So it's like saying like, you know how like, in the back of the minivan,
Like,
it has like the picture of like kids,
yeah.
and then the different sizes of the kids, and maybe one's dogs. That's essentially what we did, right? So they look, and if they see like big Jupiter, smaller Saturn, when they see those four in order, they'll be like, oh, that's the right system.
So by using both items as a reference.
Yeah, so first look in this area, find the solar system, and we're the third planet of 9, right? Well, not anymore. Well, we're still the third of whatever number, but there's no other planets in between, thankfully. Right? It would suck if we found some like hidden planet, right? Now,
What if X is long and then like it's
Shooting it like.
we're fucked then, right? It's the best that we can do at the time. Okay, so what do we think, folks? Raise your hand for yes. Raise your hand for no. Okay, now fight.
Right.
Who wants to defend their argument? Hold on now, hold on.
the pulsar has like lights coming out of both sides.
Mhm.
I mean, like you could see that from the side. Like, let's say like you're like to the left of it.
Okay, so this is my pulsar, right?
Yeah.
Okay. So can you see it?
You shoot in your eye now. Good.
No, I'm not gonna shoot in your eye. Right? Is this a way to have the pulsar so that you can't actually see it?
But I mean, can't you still see it though?
What's that?
Shoot down the middle of the room.
No, because I'm gonna hit David in the eye.
No, middle.
The middle, like this.
But can't you still see it with like on that infrared?
You can see it where it lands,
Yeah. So
but you can't see it along the way. So the only time you see it is when it's right in your eyeball, and I'm not gonna do it. Don't be like excited to get lasered. So then as it goes to your eye, right, then you see it. So we see the pulsars that are pointing towards us. So in fact, it's very possible for neutron stars to appear to pulsars to other civilizations, but not to us, and vice versa. So if you remember anything about the triangulation of earthquakes, you only needed 3 places. to find that place that they intersect. But if you look at the plaque, you'll see many more than 3 pulsars. And that's for redundancy, because they might not be looking in the same direction that we are. So you give them a bunch of options, right? And it'll show us exactly where they are. Okay, David, you ready?
Yeah.
Okay. What happens when you put too many neutrons in the same place? Okay, so now neutrons are being held apart because they don't want to be in the same state. What I mean by that, this is called neutron degeneracy pressure. They don't have charge. There's no electromagnetic repulsion. So you keep adding stuff until you get to about 3 times the mass of the sun. And then black hole. Okay, what does that mean? Black holes do not suck.
Light cannot escape that.
Light cannot escape, good. Does anything really suck? Like vacuum cleaners, yes, okay. But like in space, we think of this analogy sometimes, and we just want to make sure that we put it to bed properly. Because even though we're attracted to something like the Earth, you wouldn't say that you're like sucked to the Earth's surface, would you?
Gravity. Gravity kind of.
It goes shh. Okay.
pushes you down.
As long if we use it in that context, I'll allow it. But we don't want to think about it like a vacuum cleaner. We want to think about gravity as still maintaining the same characteristics, which is stuff falls in, but it only falls in if it's not orbiting. So for example, could I orbit a black hole? They did it in Interstellar, and we all know Interstellar is a documentary about real people who went somewhere, and it's not a fiction, right?
Now you're talking.
Correct. Okay. Okay.
Yeah.
Okay. All right. So what is a black hole? As mentioned, a black hole is something whose gravity is so powerful that even light traveling at the speed of light cannot escape. So massive star, supernova, make a black hole sometimes directly. You push all the material together and you rip space-time and you say, now black hole. Okay.
What's the difference between a black hole and a wormhole?
No such thing as a wormhole. Mathematical construct taken by people who like sci-fi and used ad nauseum to make people feel like they could travel infinite distances.
What's that?
Ad nauseum means like you use it so much and so much and so much that you start to vomit.
Okay.
Ad nauseum. So nauseum is being like ill.
Oh,
Ad nauseum is Latin for using too much.
okay.
Okay. Like I went to McDonald's and I got ad nauseum fries. Okay. So let me ask you a different question. What happens to the escape velocity of an object if you shrink the object, but don't change the mass? Are you ready? Vote on 3, 2, 1. Okay, I got some 1s, 2s, and 3s. Really good choices. Yeah, yeah. Who wants to defend their choice?
I would say that gravity is not dependent on the size of an object, but more like the mass of it.
Okay. So we're going to shrink the object. We're not going to change the mass. And we're thinking about this one, right? So what happens if D gets smaller? The force gets bigger because it's like getting closer to the center. Right? So if I can shrink the radius of something and I don't change the mass, the force of gravity goes up because the denominator is going down. Right? Same thing's true of escape velocity. So as I shrink the radius, but keep the same mass, the speed to escape that object goes up because the force is getting larger. Okay. Now there's a speed limit in the universe. What's the speed limit in the universe?
Like,
The speed of light. Can anything go faster than the speed of light? You sure? What about vibes?
Like,
Vibes go faster?
yeah.
What about emotion? I mean, you talked about Interstellar, right? Can love go faster than the speed of light?
No, I hope not. That's not-
What about quantum entanglement? Can that go faster than the speed of light?
For the expansion of-
No, it cannot. Nothing can go faster than the speed of light. Okay, it's really, really important that even though we get these feelings from pop science and from sci-fi and from people misinterpreting quantum mechanics, does not mean that we can suddenly break the laws of physics. Only thing we found so far is that this is extremely true. You cannot go faster than the speed of light. Okay, so if I keep proving it over and over and over again, that I can't go faster than the speed of light, and then someone says, but I like the idea that like consciousness is good and it goes faster than the speed of light, what would you say?
Consciousness goes faster than the speed of light.
Yes, this is what Interstellar. I was watching this film, and for 3/4 I was, this is a great film. And then all of a sudden, they put a knife into my head, my brain, they pull it out. And like, oh, I love you in the past is the future. I don't care.
It's very
I'm giving my
It's
opinion.
a very long.
You can love that film. There's nothing wrong with everyone having their own opinion. My personal opinion is that I got knifed in the brain by a film. What do you think of the market?
Oh, we can all
That's fine.
afford them.
There's no wormhole. Okay, so hold on. So let's talk about this more in more detail. So let's look at what happens at the surface, and I'll show you the parts that we got wrong in Interstellar, which is again, not a poll on whether or not you liked Interstellar. Don't care. Okay. So here's what happens. You take a star, any star, okay? Light likes to go out of the surface. Gets emitted in all directions. Okay? What?
I heard that you can see the back of your head on a neutron star because the light goes.
Yeah. Yeah. You can see your own reflection. I mean, you don't even need a mirror at a neutron star.
Weird.
You just see yourself.
You see your puddles.
In fact, there's orbits around, say, black holes and neutron stars where light goes around a circle. It's dumb. Okay. So light would not be able to escape Earth's surface if you could shrink it to a centimeter. So take the whole of the Earth's mass, 1 centimeter, right? That big, right? Okay, and the reason that happens is as you make this smaller, right? You're getting gravity to curve. Okay, and you're getting light, instead of going in straight lines, it's moving along a curved surface. We haven't really talked about this in this classroom, but gravity is an illusion. The way that gravity works is that it curves space-time, that is to say, the space between objects. So more massive things curve space more. And just like we see, like, see if I can do this well. Oh, I probably can do this.
It's.
Better ball on here. Okay. Here's the Earth. The Earth is round. Okay, it's the same.
It's
And
flat.
here's us in LA, and we want to go over here to Rome. Okay, it's a nice weekend. We're taking the weekend off. We're getting on our plane, right? Private jets only. Okay, so what's the fastest way to get there? Swim?
A straight line.
A straight line like that? No. Oh no, why not? That would be true if the Earth was flat, right? If the Earth was flat, a straight line like this would be correct, but it's not. So instead, it's like this. Because the Earth is curved. So in fact, when you look at a circle like this, okay, you want to go from point A to point B, you don't go across this line, you go across the shorter line, right? So the fact that we live on a curved Earth means that straight lines don't look straight. And when you look at space and you see something like, here's a very heavy thing, and here's this circle orbit that we're going around, that's actually a straight line in a curved geometry.
I hate that.
I know, it sucks, but that's called. General relativity, and we will not be learning that today. Okay,
Can you use that as a special topic?
you want to take that as a special topic? I don't think we're ready for that. That's gonna be hard. Okay, but the idea here is that massive objects can deform space, right? And you can think about objects as having a surface, black holes having a surface, but this is a bad analogy. And I'll explain why when we think about the process of going through a black hole. So the surface of a black hole is where light can no longer escape. It's the radius at which the escape velocity is the speed of light. But all of the mass is at the center, at a point called the singularity. It's an infinitesimal point where all of the mass is infinitely concentrated because no laws of physics work there. Chemistry doesn't work, electromagnetism is broken, gravity is broken, everything broken. Okay? And sometimes it's called the Schwarzschild radius. There's no escape. Once you pass through the event horizon, you're gone. Gone. No contact with anything that's fallen in. It increases the black hole's mass. It can change the spin of the black hole. It can change the charge of the black hole. Let's say you throw a lot of electrons, now the charge goes up. But otherwise, the object's identity is gone. Okay? So your friend, Bob, falls in the black hole. Bob is gone. Bob's gone. Bob's now a black hole. You never learn about Bob ever again. And we heard about spaghetti. Bob became spaghetti on the way in. Bob became red spaghetti on the way in. And you never saw him become actual spaghetti all the way. You only thought you saw it. I'll show you why in a few seconds. Okay? And then the black hole gets bigger. Ta-da!
I thought they said that they had seen stuff coming out.
Ah, how does stuff come out? Okay, so this is a tricky one. So black holes can lose mass.
Oh,
I
if there was
Okay. Remember when we talked about positrons and electrons colliding? Remember that? What happens when an electron and a positron collide? They annihilate and they become energy. Energy and mass are related. We talked about that. The surface of a black hole, the surface, at the very edge, you can have something where on one side, okay, one side, a positron falls in, and on the other side, an electron falls out. Yes, that's the correct space. Okay, so you can have matter simultaneously on its pair and antipair just appear at the edge of a black hole. Right. Yes, that's correct.
Like positron came in, not came out.
What's that?
Like the positron came in and the electron came out, or they both came out.
No, so they just come out of the quantum world. They just pop into existence. So they are energy, right? Just imagine energy that's held in space, okay? Not associated with anything. And then an electron just pops into existence, and a positron also pops into existence. This can happen, okay? But the reason that it doesn't happen very often is because that will immediately meet another electron or positron pair and annihilate, right? And then the energy's gone again. But in a black hole, that's not the case. So you get very weird rules at the edge of a black hole. What happens is you'll have stuff fall in and you'll have stuff fall out, and that actually gets to go on its life forever now. And this is a form of radiation called Penrose radiation, which is able to suck matter out of the black hole and let it go away forever. And it turns out that the same thing that we use for heating up peas and heating up potatoes, those rules still apply. So small black holes evaporate faster than big black holes. This is why you don't find any small ones. They evaporate like that.
So there's two sides to the black hole.
There's two sides to the event radius. Recall that it's not really meaningful to think that it's having a surface, right? It's just a point from which no light can escape. The whole is a singularity, and so let's talk about that. Okay, singularity. No known forces can resist the crusher gravity. All forces break. We call it a singularity because it really is a point. There is no inside to the point. There is no outside to the point. There is just point. And I know this is going to be really frustrating, but this is one of the things that we have to accept.
Why is there a theory of?
Why?
Yeah.
Maybe we do need to do special relativity. We can do that at the end of the semester, or maybe we can do that on Monday, depending on Wednesday. We can do it on Wednesday, maybe, if people are really interested in wormholes. But essentially, it comes from a misunderstanding of what happens when you go through a black hole. With the idea that you pass through the event horizon, and then you travel towards the center, and then something happens at the center. And my thought is that nothing at all happens at the center of a black hole, and that just like all of the neutrons that were infinitely smushed forever and ever, you are not going to make it through with your spacecraft. You will become neutrons. You will become nothing. And there'll be no more Bob. Right? That's the much more reasonable explanation. But people like, because there's a mathematical explanation that allows for a white hole and a black hole to be connected, they say, oh, that's an Einstein-Rosen bridge. It's a mathematical construct. It's garbage. Einstein-Rosen bridge. That's a wormhole. The technical term for wormhole that you see in Thor, right? And they're like, this gets us from point A to point B, right? No, no, it doesn't. Okay.
The one in contact.
What about the one in contact? That's also a good one. There's a lot of wormholes. They're all garbage.
When you say a black hole or like the event horizon doesn't have a shape, I always thought it would be like a point at the center, a certain radius that goes out with the event horizon that makes it clear. But it's not
Yes.
that way.
No, that is the right way to think about it. But it doesn't have a surface. Like I can't touch it, right?
So there's a certain distance that light can't escape.
Exactly.
It is kind of like-
That is the radius of the black hole, right? That's how we think about the radius of a black hole. But the physical interpretation is something that we have to think of separately than I would think of, say, the radius of this object, right? This thing has a surface and a radius, and it's really important not to confuse the two for a black hole.
It's not like a matter surface, but it's a surface where light can escape.
Exactly right. Does that process make sense? That distinction makes sense?
Yeah.
A really important distinction.
I don't like it.
Yeah, in fact, Einstein didn't like him either. So when he created this, he found out that these existed, and he was like, no, nature doesn't do this. I don't like it, and something's wrong, but they'll figure it out later. No, literally, he was like, this is very inelegant. This breaks down at small scales. He basically poo-pooed it. He said, Einstein made 3 major mistakes in his life, and all of them turned out to be super important.
Oh, no.
One of them was like being able to understand in detail what a black hole was. Another one was the cosmological constant that we'll begin to talk about when we talk about dark energy. So really interestingly enough, the mathematics is very robust, right? So when people are like, well, there's room for interpretation. No, there's not. That doesn't have anything to do with this. But there certainly are aliens, not for the reasons that you want there to be aliens. Okay. So here's the size of a 3 solar mass black hole. Okay. About the same size as a neutron star, right? It's not bad. I could drive across that, right?
Yeah, like 4 days.
No, you could not drive across it. Why?
Doesn't have it.
There's no surface. You can't drive across something that's got no surface. Yeah.
So does that mean there's like vacuum of space up until that radius? And then there's like just stuff inside?
There is nothing inside.
So it's vacuum on both sides of the
Vacuum everywhere.
up until the singular.
What if like a planet like ran into that, like a comet? Sorry.
A comet.
Yeah.
Okay, so we're gonna do going into a black hole very soon. Okay. So this is the geometry.
I thought you said there was no. That will make, like, they're far apart. Almost coming out from.
Yeah, so hold on, so this is going in.
Yeah.
Why do you assume that it has out?
Right there, where the things.
This keeps going.
As now,
Why does it have to have an out?
because it doesn't make sense if there's.
Yes, be uncomfortable. Be okay with being uncomfortable, right? Physics teaches us that the world is not as simple as we think it is. And that we certainly can't just hope for things to be correct, and that's the real way the world works. So here is the Schwarzschild radius. It's pretty straightforward. In fact, this derivation, you get your name for it, and any undergrad could have guessed it, right? So you just take the escape velocity, which is we write it like this for any object. V is equal to the square root of 2gm over r. So how do I derive it? Just be a light year. Square it. Put r there. Move around. Okay. Nobel Prize, please. Right? Okay, you don't get a Nobel Prize for astrophysics, so don't even try. So the thing that we want to think about here is, well, okay, this is all well and good, but you don't actually see these. Okay, these are mathematical constructions, right? That was Einstein's big argument. He's like, yes, this is a solution to the equations, but they're not real. Okay.
I agree.
So this is that example I was trying to show you earlier, is that this is flat space. Okay, and you put something heavy in the middle, it curves flat space. So this object that's going around the sun is just moving in a curved space, just going around in a straight line. And it's not actually being pulled on anything. It's just that the space that it's in is curved. Okay, and then all the black hole does is it just keeps curving space, curves it up real good, and then it rips it right at the bottom. Right? Tears the fabric of space. Okay. So if the sun shrank into a black hole, its gravity would be different only near the event horizon. Why is that? If I concentrate the mass,
Because that's one of all the masses. I thought you said there wasn't anything in the black hole.
there's not anything in the black hole. But let's look at the equations again. Hold on, where'd it go? Here's the equations. Does this have the radius of the sun in it anywhere? It's only how far away you are and the mass of the sun, right? So the force very far away is going to be the same. And in fact, if the sun became a black hole tomorrow, you wouldn't notice, except for the lack of light. You just keep orbiting. Kind of a weird feeling, right? You'd be orbiting nothing. And in fact, we see stars orbiting nothing in the center of our galaxy. Okay. What?
I hate it. I hate all of it.
It feels good, right?
No.
Okay, so let's talk about the things that are wrong and the things that are right. So first, the things that are right. In Interstellar, what happens is they get closer to the black hole when they're going to pick the person out of, like, saving him from whatever moon or something he's on. Yeah, what happens?
Oh, everything slowed down.
Everything slows down. For whom?
For the people in the.
People in the spacecraft. So people who go down, time goes slower? No, what is that? Well, we have to be very specific here. Let's think about what happens in the film. Okay, they go to save this Matt Damon, one of the many places that Matt Damon has been saved from. Okay, they arrive at the Matt Damon saving. Then they come back. What has happened? Okay, but what has happened to all of their friends and family?
Oh,
They all got really old.
and fast.
Time passed faster for whom? Okay, so more time passed for people who did not go near the black hole. Is that correct? Is that a correct interpretation?
Yeah.
And this is true. So all of the way that we think about clocks, whether that's a biological clock inside of our body, whether that's a grandfather clock. Does anyone know how a grandfather clock works? It's got a pendulum that goes like this, ding, dong, right, like that. And it turns out the period has a function of G in it, L over G, right? So in fact, if you brought a grandfather clock closer to the event horizon, time would pass differently for it. Okay. And all the clocks start to slow down, as seen from outside. So as I travel farther into what we call the gravity well, so this is called the gravity well because it looks like a well. As I travel into it, the rate at which time is perceived to be changing is decreasing. Whereas for the people doing it, they notice no change at all. So they go into the gravity well and they come back and they find out that everyone else has aged because their clocks slowed down, their internal clocks slowed down, they age slowly, but everyone else's continued at the quote unquote normal rate. That is called time dilation. Okay. Cool, right? Real. So you want to like age, just live near or age less quickly. That's what everyone in California wants, right? You just live near a black hole.
Is that because like a little spread? So,
What do you mean the well stretch?
yeah, like that well, it's long and pretty much. So, I don't know.
So what's happening here is it's called red shifting. So what's happening is the space time itself is curving here and it's stretching everything. Time is stretching. So that's what's making it longer. Okay. Okay. Is it easy or hard to fall into a black hole?
Very well.
Vote on 3, 2, 1. Yeah, I have a lot of hard votes. What do people think hard?
That's small. You said it's not much bigger than the university campus. You crazy that.
Oh, okay. So it'd be hard. But I thought, don't black holes suck?
No.
No, they don't suck. They pull like normal stars do. Right? So let's say you're aiming for it. And just like you said, you miss. Now what happens? Do you get another chance? As you fall towards the black hole, okay, let's say you miss, you're going to get slung shot because you're going to get a lot of acceleration going towards it, and it's going to shoot you back out. Try again in like 60 million years. Right? Okay. Okay. So now let's say we do. Let's say we're really successful and we're falling into the black hole. Okay. Our friend Bob. So what happens to Bob? Spaghetti. So you say spaghetti. What does spaghetti mean?
It like kind of starts ripping you apart.
So does it like pull my arms out like this and then my no hair and my little beards?
Yes.
No. What is spaghetti? It's obviously an Italian thing, huh? Spaghetti. What's that? Get thinned out?
Yeah.
Like a pasta maker. You get pastified. You become spaghetti or spaghettification. So you do get pulled apart, but in a very specific way, like spaghetti. Okay, so what does this mean?
Oh, that's a person.
That's a person. Oh gosh, that's a spaghetti man. Okay.
The black hole spins, right? And we perceive it as spinning as well.
So yeah, so let's do an example where we're very close to the surface of a big black hole, so that it looks flat at its surface. You know, the black holers there are like, you know, flat hole, right? Okay. So near this event horizon, imagine that most of it's flat here, and the gravitational pull, okay, would be stronger where? Here or here? No, where? At the toe. So it's strongest here. And how does it decrease? as you go up. So your toes are pulled more than your arms. So as you begin to fall, whatever is closest gets pulled the most. And that's a runaway process. Just like we talked about positive feedback. Okay? Again. So you go with your spacecraft. You're really excited. You're going to go through the wormhole. What do you become instead? Spaghetti.
Is that from an outside observer perspective or from your perspective getting together?
So here's my favorite part. Okay? What do you feel? Okay. So let's say, what's that?
Process happening fast.
Well, let's say we're near a supermassive black hole. Okay, the radius is going to be large and the tidal force is going to be small. But this is still that event horizon. It's not a physical horizon. So we said that a few things will happen as you enter the black hole. One, we said that it's going to look like clocks are running slower. Okay, light won't be able to escape. Is that correct? Okay. So as stuff crosses the black hole, will we see it? No. So it'll just stop ever giving us light again. And the light that just right above the surface gave off becomes redshift, becoming redder as it falls. So now let's think about us. Okay. Imagine I'm wearing a white astronaut. Yeah, I'm this dude. Okay, white astronaut. Okay. What color are my toes?
Red.
Why are they red?
You said it.
No, they said.
Space
Yes.
kind of got stretched.
So as they get stretched, the light that's coming from here is getting pulled and it's getting red shifted. Getting Doppler shifted.
Red's longer.
Because red's longer wavelengths, right? So every piece of light that's coming off is getting pulled. So will I see my toes go into the black hole?
No.
No. Will I feel my toes?
No.
No.
It's spaghetti. When your veins snap.
Yeah, so here's the question, right? You're like pumping blood around, goes down to the toes, and then the blood never comes back.
No. I never thought of it that way.
So as you become this spaghetti, another thing that happens, okay, your nerves. How do your nerves work? Do people know?
Electrical signal.
Electrical signals. Can those electrical signals go faster than the speed of light? No. So do you feel pain from your toes?
No.
No. So you don't feel anything. You just spaghetti. Everything is spaghetti.
Spaghetti.
Okay, does that make sense?
Yeah.
Okay, so now you know what it's like to cross into a black hole. And everyone who tells you otherwise is a liar.
Astrologer.
What's that?
Astrologer.
Astrologer. Yeah, they're all trying to get money from you on Instagram, okay? All right. So, oh, that was a little too fast. I'm going to show you a visualization. This is what happens when you fall into a black hole, as demonstrated by physicists who do this type of modeling. The only place where it gets a little sketch balls is when you cross through. Now, why do I say that?
No one knows what it looks like.
Bingo. We can't possibly know what it looks like inside of a black hole. This is by definition an unscientific question. In the same way that is there God is unscientific, is the color blue the best? Not a science question, right? This is also true. What happens inside of a black hole stays inside of a black hole. The ultimate Las Vegas. Okay?
Oh, that.
Of all time. Of all space. Okay, you ready? So the couple things you're gonna see here, just so you're aware, this is us. We're gonna cross the black hole's event horizon, and then we're gonna go inside of it. These are background stars. The resolution is gonna get better when I play it. And you're gonna see bending. So this is the orientation of the galactic plane. That's the disk in which all the stars are gonna live, and it's gonna be distorted. That's because as light is coming from these stars, it goes around and then comes back again. So it gets nice and squished. Okay? Over here, you're gonna see time. Okay, you're gonna see time for an observer, and you're gonna see time for yourself. See if this works. Come on now, don't fuck it up, Mateo. Come on now. Don't be broken. Let's go. Okay. Now, these are straight lines on the surface of the black hole that you'd be able to see if you could map it. So you're seeing both edges of the black hole because light bends all the way around, right? So you see both poles. And now we're getting, these are these orbits where you could be a flat circle of light going like this, not flat circle, circular orbit. And this is where we start to cross the event horizon. Okay, so these here, these white lines are what give rise to the, oops, that was it. We can see it more slowly. Do you want to see it again? Again. Slow motion. Do it again, Krismani. Okay. All right. So first of all, very far away, what do you see?
Circle.
Are you serious? Okay, this is actually gonna drive me crazy. Look what it just did.
Why don't you just update it?
I update this computer every day. Okay. Okay, so look very far away, right? You basically don't even see the black hole. Right? So this is exaggerated. Most of the night sky does not look like this. So they place it intentionally on a very bright background. And that is in order to see this distortion. So depending on the size of the black hole, you have more distortion. So if, for example, you had a massive galaxy, that would be much more distorted. And we see versions of this called gravitational lensing. This is the process of using gravity to focus light. So here, this ring of light is this image focused around the black hole. Okay. Let's get a little closer. Let me know when you want to pause or you have questions, okay? We'll run through it again. What's that? No, you are doing the white hand, and this hand is what they see your clock as. Right? Your clock seems like it's getting slower and slower and slower as you go in, because you continually look like you're getting redshifted. But for you personally, your clock is just going, right? Well, not just, I mean, they speed it up because you have to get in. Right? They can't use equal time steps at every location.
Those lines basically saying that you're seeing everything around you.
Yeah, so these ones here, as you enter the surface of the black hole, let's look at it over here. That was back here, right? That was before the white lines show up. Okay. You have what are called space-time lines, which connect everything that you could have ever done, moving less than the speed of light. So you have a limited access to space, given the fact that maybe you're 20 years old, 19 years old, okay? And that connects basically a cone of all possible locations, right? And those are the ones that are in front of you, okay? Those would be your white ones. And the ones that behind you would be your red ones. Okay. Inside of a black hole, the idea of the white hole is what happens if you were to keep going and connect that geometry on the other side. Does that make sense? No. How to explain better? It's not gonna feel good. I think we'll have to do it on Wednesday with like actual space time, but you have to understand what space time is first for special relativity. But essentially, what we're talking about here is okay, so you have a light cone. Okay, this is everything that you could live in, right? This is time this way, this is space this way. Okay, it's a time-space diagram. Let's draw it. Oh, I hate that one. Oh, that's gross. Can I have the lights, Caesar? Thank you. Okay. So let's imagine a world in which this is time. And this is space. This is going to be a two-dimensional world. Okay, just time and space only. And we can connect these because if we're, say, moving at the speed of light, right? You start at the origin, right? And then you go out like that, right? That would be CT. C times T. Okay. And if you're moving less than the speed of light, where do you go? What's that? No. E's would be less than the speed of light because you don't get as far. Okay. And if you're not moving at all, then you're going this way, right? Your position isn't changing. So this is the idea of a light cone. Because I could be going in the other direction, I could be going minus CT. Okay. And then you could turn that around three-dimensional. So you have this idea of a light cone. Okay, so all of your available world is in here. And everything that happens outside of there, you don't have access to. Okay, so we can flip this over and imagine all of the possible paths for something going into a black hole are going to converge at the singularity. All of the paths have to go to the same place. You cannot get out, right? So you could connect these lines like this. Time is going that way. All of these lines are converging at this point. The white hole says that there must be something here on this side that's on the other side of the black hole. No, that's just still increasing time. I didn't put the origin anywhere. I'm just saying that they have to go through this point.
What's falling in would be below the X.
Yeah, us falling in here, so these curves here are always straight, right? So that they're straight like that. So this is less than the speed of light. Going in, I gotta go through this point. Once I go through this point, people say, well, I like straight lines, so must keep going. And that's the white hole hypothesis. And that is
Done.
okay, good.
Oh, actually, I didn't even see it.
She's got it. She's got it. Does this make sense now? Was that more helpful, or did I lose you all as well?
No,
Okay. Okay. What happens to the radius of the event horizon when you add mass? Increases. See it over there? What happens to the event horizon when you decrease the mass? Decreases. Good, good. Okay. So to verify that there is a black hole, you need a couple things. You got to measure the mass. You can use orbital properties of a companion. You can measure the velocity and distance of the orbiting gas, right? And so you can tell it's not a star because its mass exceeds the neutron star limit. And it's compact. They say it's too small to be a star. Have you ever seen a black hole?
We see stuff
Yeah.
orbiting black hole.
We have seen a black hole. For the very first time we saw a black hole, and it looks like that. Can you show that off again? Sorry. Yeah. I have a better picture you can take.
So is that right? So, yes.
Yeah, so what am I looking at? So this is not the black hole itself. Black hole's in there.
isn't the price event?
Can I see the event horizon? It's a lack of light, right? Remember that image we just saw, right?
Oh. Yes.
Empty hole, right? In the middle. You can't see the black hole. So what is all that stuff around it? This is material that's falling into the black hole and it's getting hot as it falls. Not surprisingly, it's red. Right? Very bright, very hot, very red. Okay. It's gonna seem like a weird aside, but I'm gonna just walk you through it. I think we have time. We have 1 minute. There's a binary star called Algol. Consists of a 3.7 main sequence star and a 0.8 red giant star. 80% mass of the sun, red giant stars. What's weird about that?
Because it's a red guy.
Red giants aren't that small, right? That's weird. So how did it happen? Well, in fact, remember that most stars are not like ours. They mostly have a friend. Majority of star systems are binary. 2 stars forming at the same time, being besties forever. Okay? So one of them might have gotten too big and was too close to his friend. And then his friend starts sucking material off of the bigger companion, right? This can accrete into an accretion disk like we saw before, becomes flat, falls in, heats up. And so you start with something like this. This one goes red giant, and then it starts feeding. And then this one now has enough material to start igniting. And the companion star is more massive. And then what happens next? If this gets too big, this is, say, a white dwarf getting too big, it explodes, right? So his friend keeps feeding him alcohol, even though he's already drunk. He's feeding him, boom, disaster. The house is ruined, right? Does that make sense? It's a bad analogy, but it's kind of funny. Okay, and that's exactly what's happening here in Cygnus X1. So likely what you see is a compact object. You can't see the actual object, you can only see the accretion disk as it falls into the black hole, and it formed from this type of binary system. Questions? Now you all fully know black holes? Okay, thank you all. What's that? We can't talk about quasars. They're boring though. You like quasars? I don't really like galaxies. Galaxies are pretty boring. We'll talk about them at the beginning of next class, and we'll talk about the different structures. But for me, it's mostly just different. There's lots of people who understand it a lot better than I do, so I'm sure that they can give you a better understanding of it. But for me personally, there's just not as much texture, not as much interest.